Yo, video 12-3. Water. Molar heat of fusion. Molar heat of vaporization. So, heats of fusion and vaporization. Okay, you know that fusion is melting, vaporization is changing from a liquid to a gas. Okay, heat is required for each one of these processes. Okay, how much heat? Well, it's defined by what's known as the molar heat of fusion. Okay, and remember, whenever you see the term molar, that means by definition for 1 mole. Okay, so how much heat do you need to melt, basically go from a solid to a liquid, for 1 mole of a substance when the substance is already at its melting point? The temperature has reached that temperature. Okay, and for heat of vaporization, same thing. How much heat do you need to vaporize to go from a liquid to a gas? Okay, and the substance is at its boiling point. Now, for water, okay, well, first of all the energy added goes towards breaking the intermolecular attractive forces. None of it goes towards raising the temperature. Okay, and the units, kilojoules per mole. Okay, and the values for different substances depends on the strength of the intermolecular forces, because that's where all the energy is going. Stronger the force, larger the value is going to be. Okay. Now, molar heat of solidification. Remember, when a substance solidifies, when it goes basically from a liquid to a gas phase, you have to release energy. Okay, and the substance has to be at its freezing point. And we also have heat of condensation. We're going from the gas phase down to the liquid phase, and again, this is when the substance is condensing, okay, for 1 mole again. Okay, now the heat of solidification is basically the opposite but the same value as the heat of fusion. Okay, and heat of vaporization will have the same value but the opposite sign for the heat of condensation. Okay, now for water, when the temperature or when the pressure for the water is at 1 atmosphere, okay, the molar heat of fusion, how much heat it will take to melt 1 gram of ice or 1 mole of ice, 6.009 kilojoules per mole. Okay, to vaporize it, it is a lot more, 40.79 kilojoules per mole. Okay, why? Here you're only slightly weakening the forces. Here you completely break the forces between the particles. Here, when you go from a solid to a liquid, there's still attractive forces. When you go from a liquid to a gas, pretty much all the attractive forces have to be broken. Okay, so we can say for 1 mole of water, you want to melt it, it requires 6.009 kilojoules, and for 1 mole of water, when you want to boil it, 40.79 kilojoules. Okay, we got equalities, which means you can do dimensional analysis. Okay, so how much heat would be needed to melt 3.5 moles of water at its melting point? Okay, all we need is do dimensional analysis. 3.5 moles of H2O times, and dimensional analysis, get rid of moles of H2O, and we want to change it into heat, which is going to be kilojoules. Okay, and we go back and we look, 6.009 kilojoules is equal to 1 mole. Okay, so 6.009 kilojoules equals 1 mole. Okay, and all you have to do is just finish up the math. Okay, and this should come out to be, in terms of sig figs, just 21 kilojoules. Okay, what if we want to melt the substance, or sorry, boil the substance? Okay, again, the temperature of the substance has to be at its boiling point. So, again, 3.5 moles of our H2O times, and now we want kilojoules, get rid of moles, 1 mole of water requires 40.79 kilojoules. Okay, and this will come out to be, in terms of sig figs, 1.4 times 10 to the second. Oops, 10 to the second kilojoules. Okay, cancel our units out. Okay, now, what if I didn't give you moles? What if I gave you grams? Well, simple. Just do a conversion of grams of H2O into moles of H2O first. then you can use our equality between moles and kilojoules and go to kilojoules. Okay, now water has a lot of unique properties to it. Okay, first of all, structure of water. Okay, well, water we know, you should be able to draw its structure. It's a bent molecule, okay, and you have two non-bonding electrons. Okay, because the electronegativity differences are pretty big, hydrogen is positive, the oxygen ends up being negative. Okay, and this angle right here is 105.5 degrees. Okay, now properties of water. Okay, it's a polar molecule, we know that. Strong hydrogen bondings. Don't forget, hydrogen bond, you have to have an H bonded to an O, an H bonded to an F, or an H bonded to an N in the molecules, and then the molecules, different molecules, could bond to the hydrogens. Okay. Molar mass, 18.02 grams per mole. Okay. Now, it's a liquid at room temperature. Okay. Why is this unusual? Well, let's go take a look at some other molecules like hydrogen, nitrogen, methane, which is CH4, carbon dioxide, CO2. Okay. Molar mass for hydrogen is around 2, nitrogen is around 28, carbon dioxide, that's 32 plus 12, gives you 44. Methane gas, that's about 16. Okay, oxygen or water molar mass lies someplace in between. All of these are gases, yet water is a liquid at room temperature. Okay, so has a relatively low vapor pressure. Remember, vapor pressure is pressure caused by evaporation of a liquid. Okay, why is that? Because of the strong hydrogen bonding. Okay, that's why the substances, all the water molecules stick together. Okay, density of water. Okay, we said we kind of consider density of water to be 1.00 grams per cubic centimeter or grams per ml. Okay, but that's not true at all temperatures. That's only the density of water at 3.98 degrees Celsius. Okay. Ice, you notice, has a pretty low density, lower density than the liquid phase. Okay, that's why the solid is less dense than the liquid. That's why ice floats. Okay. Now, between 0 degrees Celsius and 3.98 degrees Celsius, you notice that the density increases. Okay, what happens to the density once you get above 3.98? Well, then the density will start to decrease. Liquid water actually starts to become less and less dense. Okay, not by much, but its density will decrease. Okay. Now, what's the structure of ice? Why does ice expand? Okay, be able to draw this structure. Ice, basically, these are the oxygen molecules in water. They form a hexagon. Okay, so here's a hydrogen, here's a hydrogen, here's another hydrogen sticking out this way, there's another hydrogen sticking out this way, hydrogen going this way, hydrogen going this way, one going down, one goes this way. Okay, and the hydrogens always point in the same general direction in terms of clockwise or counterclockwise. Okay, and the other hydrogens point outward. Okay, so what happens? This hydrogen bonds to that molecule, that hydrogen bonds to that oxygen, this hydrogen bonds there. Hydrogen bond, and hydrogen bond. Okay, so it basically makes a hexagonal structure, okay, a hexagon. Now, what's in the middle? Empty space. Okay, so why does ice become less dense than the liquid form? Basically, because it expands. So volume increases when ice freezes. Okay, now you can copy this or go look on the website. There's a link directly to it, but this is a pretty cool example of some properties of water. Okay, now your review question. Okay, how much heat must be removed to condense 3.5 grams of steam at its condensation point? Okay, so copy down the problem, do some calculations, and figure out which one of these is your correct answer. Okay, and in the explanation, you don't have to tell me exactly what you did, but make sure you tell me what were the steps that you followed to solve this problem.